In this video, what I want to talk about is how we can compare slope and rates, and how we can use the ideas that we know from slope to solve problems that are involving rates. So before we start talking about rates and rates of change, what I want to talk about first is slope. What slope is, what kind of different slopes do we have, how do we calculate it? Once we know that, we're then ready to move that into rates. So as a reminder of what slope is, we have two different formulas for slope that we often talk about. The first one is that slope is equal to rise divided by run. The other one that you may see is slope is equal to y2 minus y1 divided by x2 minus x1. We tend to use this one when looking at graphs, or that's kind of when I tend to use it anyway. And I use this one a lot when I'm given coordinates. So when we're looking at two specific coordinates and I have two x values and two y values. When we start talking about slope, there's kind of four different types of slopes that we have to be aware of. And I always remember them by using what's called slope man. So I'm going to draw slope man for us here. And then I'm going to explain what that means. So here's my slope man. Yay. Okay, so there's four different slopes that we talk about. There's positive slopes, and positive slopes, when I look at a XY axis, slopes that are positive will kind of look something like this. They're going to be increasing. As X increases, Y will also increase, hence the eyebrow on slope man. For negative slopes, what we're looking at on an XY plane is something that looks like this. As X increases, Y is decreasing, hence the other eyebrow on slope man. The other one that we talk about as well is what's called undefined. So when we look at an XY axis, and I have a vertical line, when I think about this as rise versus run, rise could be a whole bunch of different numbers, right? If I look at rise could be a whole bunch of different numbers, right? Like if I look at two different points on this line, the rise is going to be some amount, but the run is always equal to zero. Well, if the run is zero, I'm dividing by zero, and we can't do that. So vertical lines are undefined, looking at slope man. The last one that we got is on the XY axis is zero slopes, and that happens when we have horizontal lines. So very similarly, if I take any 2 points on this line, the rise is going to be zero, and the run will be some amount. No matter what, though, if the rise is equal to zero, zero divided by anything is zero. So here's where his little dimples come in. They look like zeros, and his smile is a horizontal line. So slope man is the way that I remember all four slopes. So again, we have positive, we have negative, we have undefined, and we have zero slopes. Now that we've kind of got this little bit of review of slope, let's use those ideas when we're looking at rates of change on a graph. Here I have two graphs. Determine the slope of the following linear functions and state their slopes as unit rates. Okay, so what we want to look at is what's going on in the x and y axis. On this first graph, what I have on the x-axis is time, and it's being measured in hours. And on the y-axis, I'm talking about distance, and it's being measured in miles. In order to find the unit rate, what we need to do is calculate the slope. So to calculate the slope of this line, I'm going to use any 2 points that I know. I know this point here, and I also know that point there. What we want to look at is determining the rise and the run between them. So the rise and the run are always going to create this right angle triangle. And so the rise in this case, we're looking at going up by units of 1 on the y-axis. So this is going to be 3 miles. And the run, we're looking at hours. So we're going from point 2 to point 8. So this run would be 0.6 hours. I'm purposely including my units here. So when I think about slope being rise over run, the rise of this graph is equal to 3 miles. The run of the graph is 0.6 hours. What we want to do is divide those two numbers. When we divide them, what we get is 5. And here we're going to get our unit rate. This means that we're going to travel 5 miles per 1 hour. And there is my unit rate. I can also see this unit rate on the graph. If I look at this point here, what it's saying is that after 1 hour, I will travel 5 miles. And that just kind of makes sense with the answer that we have found here. I want to show this example as well using the other formula, just to kind of show you how you could use either one when it comes to a graph. So let's kind of start this question over. The other slope formula reads slope equals y2 minus y1 divided by x2 minus x1. So what we need to do here is, again, find two coordinates. It's very similar to what I was just doing. Let's use the two coordinates that I had before. Here we had a point at, in terms of a coordinate, at 0.2, and the y value here is equal to 1. My other point was up here. The x value at that point is 0.8, and the y value is equal to 4. What we want to do is use these two coordinates in the formula below. So I'm going to give these values. I've got x1 followed by y1 because I have an x value followed by a y value. And then I have a second coordinate, x2 followed by y2 because I have an x value followed by a y value. All you really have to do here is now just plug in your numbers into the formula. So y2 was 4 and y1 was 1. x2 is equal to 0.8 and x1 is 0.2. Here what I'm going to have, 4 minus 1 is 3, and 3 is being divided by 0.6. Let's try plugging that into our calculators. This is exactly what we just did before. And again, we're going to get 5. So we're going to have 5 miles per 1 hour. And we can get that answer using both slope formulas. Let's look at the other graph now. So the other graph, now again, same idea, we need to find or start with 2 points. So I'm going to use this point here, and I'm going to use that point there. It does not matter what point you use. I obviously would recommend that you use a point that goes right through some type of hash mark so you know its exact values. But the actual points you pick will not matter. When you do the division, you're going to get the same answer. So let's compare rise versus run for this particular line. The rise is I'm now going down. So this is going to be a negative value. I'm going from here to 700 and it's stopping there at 400. So I've gone down $300. When I go to the right, I'm starting in February and I'm going up to August. So that's going to be 1, 2, 3, 4, 5, 6 months. And now we can use that to calculate our slope. So slope will be equal to rise over run. The rise that I have in this graph is that I have gone down, or I have decreased $300 divided by the number of months, which was 6. When I go and divide these, what I'm going to get is negative $50 per month. And that is how you calculate slope from a graph. Let's try a different example that maybe doesn't have a graph and it looks a little bit different. The following chart describes the number of plastic packages used at a local distribution center per year. This company is aiming to reduce the number of plastic packages they use. Determine the rate of decrease in plastic packages from year to year. Which year did the company reduce their usage of plastic packages the most? So in this case, we haven't been given a graph and we've been given a table instead. I could draw a graph that represents this information. And what I would use is that the year would be on my x-axis and the plastic packages we use per million would be in the y-axis. So how we can treat these is a bunch of x values and y values. So if we're looking at what was the rate of decrease from year to year, we're going to have to do a whole bunch of slope calculations. So let's start with the first one. Here we have slope is equal to y2 minus y1 divided by x2 minus x1. So let's first compare 2017 and 2018. The y values were 80.4 and 81.3. So let's treat this as y2 and this will be y1 and this over here will be x2 and that will be x1. Now all we need to do is plug this into the formula. So we're going to have 80.4 minus 81.3 and that will be divided by 2018 minus 2017. Let's plug that into our calculators. What we're going to get in the numerator is negative 0.9, and in the denominator, this is going to be 1. When we think about what the units here would be, remember what the y values were. This is talking about the number of plastic packages in millions. So this is meaning that we're decreasing by 0.9 million plastic packages. In the denominator, what we were talking about was years. So in this case, we decreased by 0.9 million packages in that 1 year. Let's compare this to the other years. It's going to start very similar. Now that we know our y2 and our y1, all we have to do is plug that into the formula, followed by x2 and x1. So let's go with 79.6 minus 80.4. divided by 2019 minus 2018. Notice how it's very similar to what we were doing before, but now we're just dealing with different numbers. When we subtract this, what we get is negative 0.8, and that's going to be million packages. And then again, the denominator is going to be 1, so per 1 year. And then let's do this one last time to go from 2019 to 2020 so that we can see which one did they reduce the plastic packages the most. All right, so what we'll have this time is 79.3 minus 79.6, and that will be divided by 2020 minus 2019. And what this will be equal to is negative 0.3 million packages per year. So then when we're looking at which year did they reduce their plastic packages the most in comparison to the year previous, well, that one would be the very first year. Here's one last example where we're not looking at a graph or a table of values, but we can still use the idea of slope to help us come up with a rate of change. So you are driving from Edmonton to Lac La Biche. Your odometer reads 35,017 kilometers when you leave Edmonton, and it reads 35,250 kilometers when you arrive in Lac La Biche. You left Edmonton at 3:15 p.m. and you arrived at 5:34 p.m. What was your average driving speed? What we want to start here is with our formula for speed. So speed is equal to distance over time. What we want to look at and how we can compare this to slope is what we know is that slope is equal to rise over run. So we can treat the distance as our rise, and we can treat the time as our run. So when we're looking for velocity, it's kind of like looking at the slope of a distance time graph. So here's what we have. I have two distances, I have two times. Distance 1 was what was on my odometer at the beginning, and distance 2 is what was on my odometer at the end. Time 1 is what time it started at, when did I leave Edmonton, and time 2 is when I arrived in Lac La Biche. So if we think about the slope formula, what we're going to be doing here is taking d2 minus d1 divided by t2 minus t1. I know distance goes on the top because of the formula that we started with at the beginning. So d2 minus d1 will be equal to 35,250 minus 35,017. When we subtract these two, what we get is 233 kilometers. Perfect. When I go to subtract T2 and T1, we're going to be careful that we're talking about hours versus minutes. So we're really subtracting 534 and we're taking away 315. We want to be really careful here. In this case, this is a nice example. The difference between 3 o'clock and 5 o'clock would be 2 hours. And then the difference between 15 minutes and 34 minutes is 19 minutes. In order to be able to put this into the formula, I need a number that puts 2 hours and 19 minutes all together. So we kind of need to do a little bit of a side calculation with this 19 minutes. We need to be able to compare that and convert it into hours. So we know that 60 minutes is equal to 1 hour. And what we want to know is how many hours is 19 minutes. Here's our cross multiplication coming up. So when we cross multiply and divide, we're going to multiply the two numbers that are diagonally across from each other. So 1 multiplied by 19, and then we're going to divide by the third term that's left. So we'll have 19 divided by 60, and what that's going to give us is 0.316 repeating, and this will now be in hours. So T2 minus T1 is also equal to 2.316 repeating hours. Now that we have these two things, we're ready to calculate our our speed. Speed will be equal to 233 kilometers divided by 2.316 repeating hours. When we put that into calculators, what we're going to get here is 114.68, there's some decimals after that, kilometers per hour. And then we are done. I hope this helps you solve problems involving slope and rates of change. Please let me know if you have any questions.